right, so chapter 3, what I want to do is just mention a couple of the things that we're going to find in chapter 3. I'm not going to go through examples of everything in there. Again, we're still talking about review. But a couple of things I just want to comment on that it talks about. Certainly chapter 3 talks about the mole. I hope you remember that. I think we've already had to use the idea of the mole and, you know, the fact that you can convert from grams to moles to molecules and all of that stuff. I'm not going to bother to show an example of that. It also talks about molarity. What's molarity? Moles over liters. And so it's a way of describing the concentration of a solution. It talks about how to make that. If you wanted to make, for example, a 3 molar solution and you wanted 1 liter of it, you would need to find out how many moles you would need and therefore how many grams, because we don't have a molometer to mass that out for you. So that's something to think about. I am going to bring up the idea of empirical formula. Your book calls it simplest formula as well. And that's something that you had to do on the last lab. But some of you took many of you took sort of a very straightforward approach that I'm going to chat about here for a second. And some of you kind of went around it and ended up getting the right answer, but did it in a way that you knew, for example, there were only 2 copper iodides, so you compared those to your data. If you don't know what the actual formulas are, you want to go about it a little differently. So if, for example, you could be given some information about the various masses that are in a compound. And let's say, for example, you were given 8.81 grams of copper and 1.181 grams of oxygen in a compound, and you want to know what was the simplest formula. Rather than thinking, oh, well, I know the 2 different copper oxides that could exist, what could you do to those masses? What would be a way to get to the simplest formula? Marie Louise? Yeah, so first thing you might do is to convert it into each one of these into moles. I should have left more space here. So with the copper, use the molar mass to convert it into moles, which I have calculated. I assume you could do that as well. You could do the same thing with the oxygen. Why am I not using O2 when I'm talking about a compound? Because some of you got stuck on this, that iodine was diatomic on the lab. Why am I not using it? John? Yeah, it's not diatomic when it's in a compound, period. There may be 2 of them, but that's not diatomic. There may be 1 of them. There may be 3 of them. So inside of a compound, it's just oxygen. So then I get these numbers, for example. What do I do with these numbers now if I'm trying to find the simplest formula? What do I do? Most of you know. Or maybe you don't know. Smriti? Yeah, so I'm going to take these each and divide by the smallest number of moles. Wow, can't write today. To see what that mole ratio. Obviously, this one's going to be 1, and this one ends up being around 2. And so our formula then is Cu2O. 2 coppers for every 1 oxygen. What if you were given the percent composition as one of your blues problems for today? We'll give it to you. So what if, for example, you were told it was 79.9% copper and 20.1% oxygen? What would you do then? Aditya? Yeah. Right. So then we can assume a 100-gram sample, which then would make it 79.9 grams of copper and 20.1 grams of oxygen, which we could then convert into moles and divide by the smaller. Sometimes when you do this, for example, up here with this 2 to 1, it doesn't work out to be a nice, neat whole number. If it works out to 1.5 to 1, what are you going to do? double it. I mean, you got to get it to be a whole number. You're just seeing what that ratio is. Okay, so we okay with that? I think number 44, you got to do that. Okay, that is the empirical formula. That is the simplest whole number ratio. It is not the molecular formula. If you need to find the molecular formula, you need more information than just this, like what is the molar mass of the compound, for example, so you can figure out how many times larger it is. All right, another thing in this chapter, this is all I'm going to say about it. This is in the chapter, balancing equations. You should know how to do that. Okay, moving on. Number 4, your good friend stoichiometry. Remember, limiting reactant, excess reactant, percent yield, that kind of thing, which when you learned it in Chem 1 the first time, it was making you pull your hair out. Now you'll think it's no big deal. All right, so let me just give you a very simple problem just to remind you, because for some of you it's been a little while. Some of you it hasn't. So let's say we have this balanced equation. We have solid sodium, some chlorine gas, turning into solid sodium chloride, which is not a gas. Ooh, it's a solid. And then let's say that you're given, let's say you have 50 grams of solid sodium. And let's say you have 50 liters of chlorine gas at STP. Like how I threw all that out there? Let's just get it all done. STP, what's that? Standard temperature and pressure. And we would like to know, based on that information, how many grams of sodium chloride are we going to make? All right, what's a basic idea? What's a nice simple way to figure out who is limiting reactant? What can we do with the 50 grams of sodium? What can we convert it into ultimately? Hayden? Convert it into moles, then where? Where are we going to go to the end? Yeah, it's a really nice, easy thing. Since we're trying to find this, convert in each of our individual reactants into the product we're trying to find. So in the case of the 50 grams of sodium, we certainly can do that. I guess I'll set one up here. And so we can convert grams into moles of sodium. Then using our balanced equation, convert moles of sodium into moles of sodium chloride. And I would go, you don't have to yet, but I would go right to grams because ultimately you need to figure that out anyway. So 1 mole of sodium chloride is 58.5 grams. And I calculated this, got 127 grams of sodium. Which is not my answer because I don't know if sodium is my limiting reactant. So I can do the same thing. I have 50 liters of chlorine gas. What am I going to do with that? I would like to turn it into grams of sodium as well. How am I going to convert 50 liters of chlorine gas there? Laren? Okay, so we can do a little PV equals nRT business, right? Because we know the volume. What's the pressure? 1 atmosphere because it's STP. What's the temperature? 273 Kelvin. All right, do you remember R? 0.08206. What are the units? I know it's been a while for some of you. What are the units? Liters, atmospheres per mole Kelvin. Now you know. That's not the only form of R. Of course, there's the 8.314 version. That is different units. I suggest you look them up. Okay. But here, since everything is given already in liters and atmospheres, I would go ahead and use this version. And you certainly can solve for the number of moles. So that's one way that we could get number of moles of chlorine. What is another way we can get number of moles of chlorine? Hayden? Yeah, or if you happen to remember that there's 22.4 liters per mole of gas at STP, which we are. If you're not at STP, this number doesn't work. But if you remember that number, you can also use that. You will get the same answer. I'm lazy. I'm going to use the 22.4. So I know there's 22.4 liters of gas in 1 mole of chlorine because we are at STP. And now the rest of it becomes pretty simple. So there's 1 mole of chlorine for every 2 moles of Cl. 1 mole of NaCl is 58.5 grams. I compute that. I get 261 grams of sodium chloride. So how much sodium chloride can I make? 127 grams of sodium chloride. Who is my limiting reactant? Sodium is my limiting reactant. Who's my excess reactant? Of course, it has to be chlorine here, right? All right. Of course, that leads to other questions that I would just like to remind you about, but I am not necessarily going to work out completely for you. Well, this first one we can because it's simple. Here's a follow-up question. If 115 grams of sodium chloride are actually produced in the lab, what is the percent yield? What is the formula for binding percent yield? Marie-Louise? Yep. So it's actual yield over a theoretical, the theoretical as in the math, right? Times 100. So in this case, the actual yield is what number? The 115. So 115 grams divided by, I don't know, 127. 127 grams times 100. I don't know. I didn't calculate that one out. What is it, Chaina? Say it louder, like I'm old. 91%. 91 point what? Oh, well, how many sig figs should we have now? What a good question is that? 3. So what is it with 3? 90.6%. Okay, so there's our percent yield. How we doing? Guys okay? I know I'm zipping through it, but this is stuff you all learned in your past. Another follow-up question. Of course, you know this one would be coming. How much chlorine is left over? There's multiple ways to get to the answer to this question. And I'm not going to work it all through, but if I kind of scale back, if I know this is limiting, then I know that my sodium, like I'm going to produce this much soda. That should say NaCl, right? Like that produces that much sodium? That doesn't make sense. So I can figure out, since chlorine is left over, I can figure out, based on the amount of sodium I had, for example, how much chlorine is it going to use? And subtract it from the amount I had. Or I could take the amount of sodium chloride I'm going to make and figure out how much chlorine was used to make it. That would be fine too. So, you know, whatever method it is, I would probably tend to take my 50 grams of sodium and eventually convert it into the grams of chlorine used, and then subtract the chlorine that you have minus the chlorine that you used to find out the leftover. My assumption is you can do that. I'm not going to show all the mathematics for that. Okay? Questions on all that stuff I whipped through really quickly? Smriti?
The last one, be asking like if theoretically how much we have left or like actually the lab?
Good question. This would probably tend to be a theoretical question. Or if it wasn't, it would be clear using the actual yield. Now, of course, could be done in grams of chlorine, could be done in liters of chlorine here. How many liters of chlorine are left over at the end? Because it's a gas. Things like that. Other questions? Okay, then I need you to open your textbook. You'll notice you have 5 problems, but I want to chat with you about 93 for a moment. All right, my first comment about number 93 is don't do drugs. You'll see why when you read it. I'm thankful that every time they switch versions, they keep it as cocaine. They couldn't have come up with something better, but yet I'm still going to make you do this problem because it's an excellent problem. However, I'm not sure that all of you are ready to solve for it just yet. Now, some of you, based on the very first lab in the year, might be. But what I want to do is to just kind of talk you through this very first problem. Well, it's not the first one, but number 93, so that you don't get stuck. My hope is to get you going on it. All right, so if you take a look at number 93, we apparently have some cocaine that's mixed with sugar. Again, I am not saying anything about drugs. You should not be doing drugs, nothing. This is simply a chemical, which we will allude to the cocaine problem for like the rest of the year somehow. All right, so we've got this cocaine mixed with sugar, and we have a 1 milligram sample of the mixture is burned. And when that happens, we get 1 milliliter of carbon dioxide that is formed. And your job is to figure out the percentage of the cocaine in the mixture. Now, if you think about it, the very first thing that I had you do, like the first day of school, was a mixture problem, right? And so that line of thinking can again be helpful here. But what I want us to realize in this problem is that in both cases, both of those are hydrocarbons. So if you take the cocaine and you burn it, which is what it says, so we're going to combust it, react it with oxygen, we're going to get carbon dioxide plus water and other stuff. But I'm only concerned with the carbon dioxide because in the end it tells me 1 milliliter of carbon dioxide is formed. Now, this is not a balanced equation. It's not even an equation yet, but you might think about how that is going to balance out. The other thing, of course, we also have sugar, which is also a hydrocarbon, which is also going to burn in oxygen to produce carbon dioxide and other stuff. What we know is that the mixture of these two together, according to this problem, weighs 1 milligram. So we don't know how much is actually the cocaine and how much is actually the sugar. So what might we do if we're interested in how much is cocaine? What might we call that? What amount? X. I want you to think back to that other lab. So I would recommend perhaps calling the amount of cocaine X. I think it's simpler to call that one since it wants to know the percentage of cocaine. What is the mass of the sugar then if cocaine is X? Madison? Yeah, it's 1 milligram minus X. Now, of course, be careful here because this is in milligrams and perhaps eventually you'll want to get it out of milligrams and into grams. But so we have this idea. So that together, of course, they equal 1 gram. The other thing is that when you add the carbon dioxide from both of those, together they have to add up to 1 milliliter. So that's something that you're going to want to consider. So as you go through this problem, you perhaps want to take the amount of cocaine and eventually figure out how many grams of carbon dioxide there are from the cocaine, and take the sugar and eventually figure out how many grams of carbon dioxide come from the sugar so that you can get the total produced. So this is just my little get you started kind of thing on 93. I assume based on this and you reading the problem a little more carefully that you should now be able to finish that problem. Okay? All right. So I achieved my goal, which was to give you a little time to work on those problems because some of them are a little lengthier. 5 doesn't sound bad except when they take 15 minutes each. then they start to sound kind of bad. I don't know, it's going to take 15 minutes each. I just made that number up. I didn't like time myself, and it took me, no. But you have 15 minutes, which means at the very least you should get one done. But you're going to prove me wrong. Some of them are shorter. You can get a couple done, and then you should only have like 3 maybe for homework. Okay, so the time is yours to work on those blues, get a couple of them done, finish the rest for homework. Tomorrow is solely a blues practice day because your test is Monday and Tuesday. I know I haven't talked about a lot of stuff in these 3 chapters, and that's because it's review. Don't worry, I will talk about other stuff when we get into harder stuff. Okay, so time is yours.